Before I get into today's worked example of a latent heat calculation, I'm just going to quickly run through the concept of latent heat so you understand this. And you will find latent heat questions often go hand in hand with specific heat capacity questions. So if you don't know what specific heat capacity is, please watch the videos I've produced on that topic. The link is in the description below, as it's an important topic in both chemistry and physics at high school level and beyond. So let's look at this word latent, or latent as sometimes you hear it. It's just another word for hidden. And the sort of hidden heat then, if you like, is usually comes about when there's a phase change. So a phase, also known as a state, is whether something is a solid or something's a liquid or a gas. So when a phase change takes place, for example, a solid turning into a liquid, which would be melting, or a liquid turning into a gas, which would be evaporation, energy is required to do that. And that's exactly what the latent heat is. So it's basically can be defined as the energy required to cause a change in state. Let's put, say, liquid to gas. Chemistry state symbols there, L for liquid, G for gas. And that's the first really important point. The second really important point is during a change in state, there is no overall change in temperature of the substance. So it doesn't increase or decrease in temperature. During the change in state, there is no change in temperature. Say, for argument's sake, this change in state is happening at 50 degrees for some random substance, right? It is going to stay at 50 degrees C when that substance is undergoing the change in state. So that's why the idea of latent heat is this idea of like hidden heat, because putting energy into the substance, a change in state is taking place, but the temperature is not changing. So it's sort of that heat is hidden. Actually, what is happening to that energy that's going in? Why doesn't the temperature change during the change in state? And the answer is this. So let's pose that as a question so you can write this down as a note. So why doesn't the temperature change? And the answer is simple. It's because the energy supplied or removed goes into sort of breaking the bonds between, I'm going to use this, I don't like this word, but I use the word particle because it could be ions, it could be atoms, it could be molecules, it depends, but just keep it vague. So it's between the particles. So let's just take the example of water, right? So you've got water molecules and they're bound by intermolecular forces. When you put that hidden heat in, if you like, the energy goes to breaking the intermolecular forces between the molecules so that it can escape. So the water molecules can escape from the liquid phase into the gas phase. In other words, they become completely separated out. So the energy supplied goes into breaking the bonds between the particles. Right, lastly, before we look at the worked example, we've got an equation for it. So we have L is the latent heat is equal to the E, as I've been using the symbol E for energy in my other videos, divided by M. So L is the latent heat of the substance and E is the energy either supplied or removed to cause that change in state, and M is the mass. So that's the equation there. So I've lifted this straight from a typical grade 10 GCSE physics paper, and it says, state what is meant by the specific latent heat of fusion melting. Going off the definitions we just talked about, it's the energy required to melt 1 kilogram of a substance under standard conditions. So what are standard conditions? That would be, in science terms, room temperature is defined as 25 degrees C. Atmospheric pressure is 1 atm, or approximately 100,000 pascals. Right, ice cubes of total mass 70 grams and at 0 degrees C are put into a drink of mass 300. All the ice melts. 23,500 joules of thermal energy transfers from the lemonade to the ice. The final temperature of the drink is 0. Calculate the latent heat of fusion of ice. So let's do a little drawing of what's going on here. So we have, just so you understand what's going on. So there's our glass of lemonade. There is a ice cube, let's call it this square there, and energy is being transferred from the lemonade, which is warmer, into the ice cube. So the energy is going, let's put some labels on first of all. So this is the ice cube, this is the drink, the lemonade, and the energy is going this way. So it's actually an endothermic process. So we need to work out the latent heat of fusion. So let's pull our equation into the screen there again. So we have L equals, the total energy put in is 23,500. The mass of the ice cube is 70 grams. So we need to turn that into kilograms, equals, round it to one decimal place, 3. Now this is the important bit. You will see line has been left blank because you have to put the units in yourself. Units would be joules per kilogram. The thermal energy that causes the ice to melt is transferred from the lemonade as it cools. The loss of this thermal energy causes the temperature of the 300 grams of the lemonade to fall by 19 degrees C. Calculate the specific heat capacity of lemonade. So now we're bringing in the formula that I discussed in my previous videos on heat capacity. So if you haven't watched them, please look at the link below in the description. And the formula is E equals mc delta T. We need to rearrange, so it's in terms of C. So C equals E divided by m delta T. M is the mass of the substance. Delta T is the change in temperature. E is the energy supplied or removed. And then C is your specific heat capacity. So the thermal energy that causes the ice to melt is transferred from the lemonade as it cools. The loss of this thermal energy causes the temperature of 300 grams of lemonade to fall by 19 degrees C. So the energy that was transferred to the ice, well, we were told this at the beginning, was this number, which I've just underlined there. It will be 23,500 divided by the mass of the lemonade, not the ice cube, because we're trying to find the heat capacity of the lemonade. So the mass of the lemonade is 300. Don't forget brackets, 300 times the change in temperature. So it decreases by 19 degrees C. So that is delta T. Gives us 4.12. What are the units this time? Well, I've just put that mass in terms of grams. So therefore I have to express my heat capacity in terms of grams. So this would be joules per gram degree C. If I wanted to turn it into kilograms, is consistent with this, well, there are 1,000 grams in a kilogram. So that would become, taking the full number off the calculator, the full number was 4.1228070. So to turn that into kilograms, that would be 4122.8 joules per kilogram degrees C. Right, finally, the melting ice floats on top of the lemonade. Explain the process by which the lemonade at the bottom of the drink becomes cold. Okay, so what this part is actually a convection question in disguise. So convection is when you have cooler, more dense, the cooler, more dense particles sink to the bottom where the heat source is, and the hotter particles expand and they rise, and it sets up this sort of convection cycle until the whole thing becomes uniform in temperature. So explain the process by which the lemonade at the bottom of the drink becomes cold. And the first point, cooler, more dense lemonade particles sink to the bottom. And remember, the ice is cold and the lemonade is warmer. So cooler, more dense lemonade sink to the bottom, and then basically warmer particles are drawn upwards to the ice cube. So if I do a little picture to illustrate this, so there's the beaker there. So the red dots are the particles. So cooler, more dense lemonade particles drop to the bottom and take its place. It sets up this convection cycle. So why do the warmer particles move to the top? And the reason why, which is our third point, is that energy, in this case heat, is always transferred from a hotter region, which is the lemonade, that bit basically, to a colder region. And the colder region is, of course, the ice cube. So those warmer lemonade particles are drawn towards the ice cube. And what does that cause? It causes it to melt. And then the cooler, more dense lemonade particles move downwards and take their place. So it sets up this as you can see, this cycle, what's called a convection cycle, until eventually the ice cube gets smaller and smaller and completely melts. And then the whole glass of lemonade becomes the same temperature, has a uniform temperature. I hope you found this video helpful. If you've had any value from this, it helps the channel massively. Just like and subscribe and pass it on to somebody else. Otherwise, I will see you in the next one.